Hello, everyone. Welcome to our third episode of Digitalization of Utilities. And today's topic is an innovative gas system of future digital twin project. And this project is quite in discussion these days on LinkedIn, and you'll find a mention of it in reports from Ofgem. We have two guests today talking about this project. We have Arvin Frank Schultz and James Hope. Arvin is overall project leader for this project from IBM Consulting, and James is the lead architect on this project from IBM Client Engineering team. And I would like to welcome both of you on this show.
Thank you.
Thanks, Nino. Great to be here.
My pleasure. And this is a quite exciting project that we have started, and I wanted to bring this up on light to see what sort of innovative ideas and what sort of innovative use cases that we are working on. So in short, Arvin, if you can give a context behind what Gas System of Future Digital Twin project is all about.
Right. In the UK, we have a lot of our houses, our domestic houses, use gas for space heating and also use gas in a lot of industrial processes. The thing is that we have to effectively stop burning at least the kind of gases that are net contributors to greenhouse gases. So that's basically the methane-based gas that we get out of the ground, natural gas. So that is to some extent an existential threat to the gas companies, but also a major challenge to the infrastructure of the country, in that if we were to move all of our gas-heated homes to heat pumps or some other form of electrical heating, that would put huge pressure on the electricity distribution networks. Many houses are not suitable to heat pumps, either because they don't have space outside the houses to put heat pumps. Source heat pumps are considerable source of noise, and the output temperature is a lot lower. And for some of our very old Victorian styled houses, which have got very small bore radiator or central heating pipes and small radiators, it might not be practical. So one of the alternatives is looking at hydrogen, either mixing it with natural gas, with methane, or ultimately replacing it. Either way, there are going to be significant changes to the gas network over the next decade or two. And part of this project is looking at one, that whole hydrogen aspect of it, and secondly, at how do we model those changes? How do we understand changes to the gas network without actually having to implement them? Because we've got, this is massively complex infrastructure that most of it sits underground. Changing it is rather complex, disruptive, and difficult and expensive. And therefore, it's always a good idea to model these things first to get an idea for different scenarios. So we can, in this project that we're doing, which is a Strategic Innovation Fund funded project. So Strategic Innovation Fund is a UKRI, UK Research Initiative Fund, that is administered to a large extent by Ofgem, economic regulator for utilities in the UK. And so as part of that project, we can address a smaller number of epics only, but so that's the bigger picture, the context which was this. So we see this as a crucial contributor to moving to net zero fundamentally.
One of the reasons that we are talking about gas more at this point of time is dependency on Russian gas. Is there any linkage to how we improve our efficiencies, replacing methane with hydrogen, and then how we build our future for the gas networks?
So it doesn't fundamentally change the underlying concept of the project. It has clearly highlighted the importance of doing this work, because up until now, or up until recently, this project was mainly focused on net zero. I think as we see the gas prices rise, I mean, the UK doesn't actually import much gas directly from Russia, but we buy our gas on the international market. Even the gas that we, in quotes, British registered companies extract from the North Sea are sold at international prices. It's an international gas market. So we've been clearly hit very hard by the gas price rises, which makes this not just not just a net zero issue, but also an economic issue, much more so than it was a year or a year and a half ago. So it hasn't fundamentally changed our project, but it's certainly shone a very bright spotlight on it, and it makes it even more important, I think.
Yeah, certainly. And then when we talked about SIF, right, the Strategic Innovation Fund, how was your journey to get those project, funded?
So it's a multi-stage process. So the Strategic Innovation Fund, SIF projects, go through 3 stages. There's a discovery phase, which is a relatively small phase where you define the requirements and so on. Then the alpha phase, which is where we're in now, which is typically £500,000 worth. And then there's a beta phase, which is what we're hoping to do next, which could be potentially a much bigger project. And yes, it's been interesting, not always easy ride. So there were quite a few digital twin projects that got funded for the discovery phase. I think we were the only one that actually made it through to the alpha phase. Clearly, Ofgem and UKRI, who are making these decisions, have got some very specific ideas. And so we were told that the reasons that we were successful was because we were looking at this from an ecosystem point of view. Digital twins don't live in isolation. They need to talk to other systems, potentially other digital twins. So we involved the energy systems operator, the ESO, currently with National Grid. We have involved a whole range of stakeholders. The other thing that they liked about our proposal is that we're building on previous innovation projects that our client in this, Scotia Gas Networks, SGN, and our partners like DNV have already done. So building on existing innovation projects rather than starting everything from scratch was another key contributor. And then I think the last one was our focus on data and making data available and also standardizing the interchange of data. And I think that those are all very important aspects, and that was the reason why we won this. Plus, I think we convinced decision makers that this is absolutely crucial if we were to want to achieve net zero by 2050 in the overall UK economy. And when we say that, I mean, our target is to have net zero in the energy system really earlier than that in 2035. So these are very challenging timescales.
Yeah, and quite crucial time and crucial project to work on, isn't it? We talked about a couple of partners. I mentioned DNV, you mentioned SGN. Who all are partners on this with you?
So we actually merged 2 discovery phases into 1 alpha phase, which widened the partnership range a little bit. So Scotia Gas Networks, SGN, is the overall lead, the gas distribution company. And then, apart from IBM, there's AWS, who provide the infrastructure services and some of the digital twin holding, if you like. So AWS IoT Twin Maker is key in this, for example. Then there's DNV, who bring a lot of domain expertise from the gas world. There is Esri, who are the leading GIS supplier in the utilities market. Then we have the ESO on board as a partner, a slightly less involved partner, but still as a partner. As a big part of this is showing how this whole cross-vector integration in the energy market is going to become important. So, converting electricity into hydrogen, potentially converting hydrogen back into electricity, and looking at how we can use this massive asset of our gas system that we have in the country to help balance the electricity system. So that rounds up the partnerships. James, have I forgotten anybody? I think those are all the partners that we've got.
I think that's right.
It's a big cross-industrial integration, isn't it? Talking to electricity system operator, distribution, a lot of partners together. So one question that comes to my mind is why digital twin? I want to understand more on how do you define this digital twin and why is this digital twin right for solving this particular problem of gas system of future?
So I don't give you a definition of digital twin, as I led an IBM, or co-led an IBM Academy of Technology initiative into digital twins with our colleague Andy Stanford-Clark. We published a paper in which we've provided actually a couple of definitions. I'll give you one of them. I'll read it out to you. I'll let James explain why we believe that's important to this specific problem. Our definition is a digital twin is the dynamic virtual representation of a physical object or system, usually across multiple stages of its life cycle. And it uses sufficiently up-to-date data, real-world data if appropriate, as input to simulation and or machine learning models which, combined with data analysis, enable an understanding of the object or system. And digital twins can be used to answer what-if questions, improve decision-making, and control the systems that they represent. I think that last bit is really important. I think we see a lot of digital twins which are just kind of I say just, I mean, there's a role for that as well, but that are, in quotes, just 3D models and look nice. For us, it's absolutely important that a digital twin aids decision-making. If a digital twin doesn't lead to somebody or something, it might be completely automated, making a better decision, then it's kind of pointless. James, do you want to explain maybe how that fits into the kind of problems I outlined that SGN need to solve?
Yeah, so one of the personas we've been focusing on is Alex, who's a hydrogen production manager. So he's responsible for managing hydrogen production, and that's not a straightforward decision for Alex. His role is minimizing the cost of production and producing hydrogen using green energy wherever possible. So to do this, he needs to consider factors such as wind generation, electricity forecast, hydrogen demand forecast, both which are directly influenced by the weather, to decide how much hydrogen to produce. He also needs to consider electricity pricing, since he may need to purchase electricity for hydrogen production if there's insufficient energy available from wind. So in the work we've been doing, we conceptualized that as a mixed integer programming problem with a cost function of electrical power and renewable power, where that's a model that we coded in Python and will be later modified to use IBM CPLEX. And what the model does is it produces a production plan of hydrogen for Alex, taking into account various constraints such as the maximum storage limit, the minimum and maximum rate of production. And so each time Alex runs the model, he's provided with a production plan based on the most recent forecasts. Alex can also run what-if simulations, so he can control the minimum acceptable level of storage. We run the model and see the output of the model against the baseline model. So this is one of those kind of key functional capabilities of a digital twin that we've been able to demonstrate in the proof of concept that we've been building in client engineering. Just to add to that, so we've been surfacing that data to Alex using Grafana, open source Grafana. We've been using IBM Cloud Pak for integration as the integration platform. And that, in many ways, is what a digital twin is. It's integration between lots of different capabilities. So the other aspect of a functional part of the digital twin that we really wanted to highlight with this persona was taking data from various different sources and surfacing that data out to Alex dashboard, which we used Grafana for.
Okay.
Yeah.
So is there any testing playground that you are going to test against for this digital twin?
Well, I think the prototype itself is really an environment for testing. We've put this in sprints, and at the end of each sprint, we've validated what we've been doing with SMEs, like for example, but also other SMEs we've been working with within IBM and also across our partners, such as DNV. And so, for example, some of the feedback we've had has raised some really good points around data assurance, for example, around open data, around the interoperability of different digital twins. I think that's where this alpha phase has been really valuable. It's given us a glimpse into what a system of the future might look like, and some of the assumptions that we are currently, it's tested some of the assumptions that we're currently making, and it's helped us to see some of the challenges that we might have in an beta phase build.
Okay, and you're assuming this particular data, right? You might be pulling data from various sources or various external stakeholders as well, like renewable electricity, how much it's generating. You talked about price control. How are you securely getting that data, or how you're integrating that external data factors securely, as well as what about the data transparency aspect of this?
So that is something that we'll probably only do in beta phase. At the moment, we are simulating a lot of data. So to expedite this very short, sharp alpha phase, we are generating a lot of our data as synthetic data for two reasons. One, the hydrogen plant doesn't exist yet. It's still being built. So that's the thing I mentioned of a digital twin progressing throughout the life cycle of the system that it's twinning. So at the moment, the system doesn't exist yet. That doesn't stop us from actually building and demonstrating the potential value of a digital twin and showing, for example, how much optimizing energy use could potentially save in terms of energy consumption, making some pretty decent assumptions about the cost of energy, but keeping the whole stochastic nature of it in place. So our synthetic data doesn't just follow a straight curve or anything like, or a straight line even. It's we've injected random noise into that to make it as realistic as possible. And so the next step would be to in the beta phase start connecting up the twin to real data feeds, replacing our synthetic data feeds.
So assuming the synthetic data feeds, so did you assume what is the capacity or demand capacity versus hydrogen electrolyzer capacity, storage capacity? Was there any assumptions behind them?
Those are not assumptions. So those are the real design points. So we spoke to the people who are designing the project. So Sarup is actually designing a lot of that. Electrolyzer is off the shelf as these things come. So they are all, to some extent, bespoke, I guess. But yes, that's a manufactured item. So it has its specifications. So the quantity of storage, the electrolyzer, its power consumption, all of that is based on the specifications of actual equipment that's going to be used. So yes, so that isn't assumed. The gas was modeled by the gas consumption. The demand was modeled by DNV based on the type of premises that will be supplied. And there are 4 types of demand: a cold winter's day, a normal winter's day, summer day, and an autumn spring day. And so we took that as the baseline and then added some noise, both the kind of daily and half hourly noise to that to create a more random data set. So that's how the data was created. So, so when we said synthetic data, we tried to make it as realistic as possible. So for example, for the price data or electricity, we took actual Elexon data for a few days and then extrapolated from that. So again, we've got a realistic shape of what the electricity price looks at on a typical day. So we have used real data as the basis for our synthetic data.
Yeah. So that data and the output of a linear model is surfaced to Grafana dashboards. And we've developed 3 dashboards. So we've got an entry dashboard, which provides a sort of situational overview of the plant, including metrics like the production rate of the electrolyzer, the current production cost, things like the current consumption of renewable power as a ratio to grid power, and the storage level. And we've also got a 3D representation of the plant built in AWS IoT TwinMaker with shading applied to the different elements of that representation of that 3D to augment the experience for Alex. The second dashboard we have is a historical view of the plant for diagnostics. And the third dashboard is a production plan for the forecast, the hydrogen plan, if you like, with information about the power source, the production cost and storage levels.
Okay. So when you started, you said that there were multiple use cases. Hydrogen digital twin is one use case that you mentioned. There was another digital twin that you mentioned was gas distribution system. Can we explore what sort of use cases have you considered, or what sort of problems are you solving for gas distribution network, considering hydrogen or biomethane been pumped in distribution channels?
Yeah, so we've been, the 2 other user stories that we looked at. So second user story is Roger, who's a gas network operator. His responsibility is balancing the gas network, and currently Roger doesn't get timely information about the operation of peaking plants. In fact, he doesn't get very much information at all, and so that's a challenge for Roger in terms of making sure there is sufficient gas in network to ensure continuity of supply. And we anticipate that in the future there'll be more peaking plants coming online, so that's expected to become an area of concern for. So information about the balancing market, understanding the impact of the anticipated demand on the gas network is important for Roger. And so one area we've looked at is surfacing that data to Roger and ensure that he's able to, again, back to the kind of what if capability of a digital twin, he's able to understand the impact on the network. And then the third user story is around Helen, who's a local authority planner. She needs to understand the development considerations around land planning. She needs to understand if connections to the gas network are feasible and whether or not the profile of a development can be met by the existing pipeworks and supply of gas through those pipes. So, in fact, we envisaged a two-stage process for Helen. So an initial feasibility check, where she would be able to draw a polygon and Esri to understand the route to the existing gas network. A second check, which would involve a calculation of a peak load, a what-if simulation in DNV Solver, which is the gas modelling tool that we are integrating with, and then to surface that data back to Esri on a map so that it's very clear to Helen and also Barbara, who is a gas network operator, the impact of that planning.
Okay, so you talked about two personas, Roger and Helen. Roger is someone who is sitting on the distribution side of a network. And you talk about peaking plant example. What exactly the challenge the gas distribution companies are facing as a result of peaking plants in an overall market?
This is a really good example, again, of cross-vector integration. So we've got the electricity energy vector and we've got the gas energy vector. And as the electricity system has more and more distributed energy resources rather than nice, big, chunky central power stations that we can control, we've got wind, solar generation at the edge, people charging EVs, potentially people having heat pumps. So it's a very demand that can kick in with huge demands at a certain time. So somehow we need to balance all of that out, and that's where these peaking plants are springing up. So these can be, as small as a shipping container-sized gas turbine that's gets connected to the network and sits there most of the year not doing much. But when there is a shortage, then the ESO will call on it to suddenly spring into action and deliver a bunch of electricity. To do that, it sucks a bunch of gas out of the gas network, which is kind of comes as a bit of a surprise. Now, clearly, these peaking plants aren't connected to parts of the gas network and can't deliver with it, but it's not always foreseeable when this happens. Gas network operator needs to every day tell the gas transmission company how much gas they want. And so in this case, for example, they need to potentially work out that if peaking plants in one area are suddenly fired up, they might need to in quite a hurry, up their estimate of how much gas they'll need. And so, it's addressing this challenge, actually a challenge which originates in the electricity network, which is being solved by these peaking plants that use natural gas-fired turbines to generate more electricity. So this is how, having a little bit of gas generation every now and then helps us to connect much more wind generation and solar. You might say, well, the gas generation is dirty. If, on the other hand, that enables a lot more wind to be connected, then overall that's still a better benefit. And then over time, we will obviously need to replace these turbines with other mechanisms, maybe storage like batteries, or fire the turbines with another gas such as hydrogen, or at least replace some of the natural gas with biogas, which comes from sustainable resources rather than from fossil resources. So that's one of the reasons we picked this, because it shows that integration and the importance of different energy vectors supporting each other.
Yeah, and it shows how dependent the energy system is on each other, right? Your electricity is more supported by, or more than 50% supported, at least in European region, is supported by your renewables. And these intermittent renewables, if they are not generating and your base load is not sufficient enough to serve the demand, then how these peaking plants are really helping to bridge that gap between intermittent renewables and the electricity demand. But then that has a cascading impact on gas distribution because it sucks a lot of gas out of it. This is quite a unique and real cross-sectoral integration use case that you're building with. There must be multiple stakeholders in this, right? You talked about ESO, you talked about peaking plant, and the gas distribution company itself. So three major stakeholders that this digital twin would be talking about, isn't it?
Yes, so those are the ones that we're considering at the moment, but this has scope for further extension. So, for example, these peaking plants are not connected into the transmission network, but into the distribution network at lower voltage levels. So, an extension of this would be to link that up with the distribution network operator that operates the network in that area to make sure that they can actually port the electricity to where it's needed, and that's not going to cause congestion issues on the distribution network. So the ESO kind of looks at the national balancing challenge that we have, dispatching a number of peaking plants in the same area might not just cause gas problems, but also distribution network problems. So as I said, it's not something we've considered yet, but that's definitely an extension and would provide yet another party to this. And then James talked about Helen. Again, the siting of these peaking plants is important in that, so they need to be near other infrastructure. So the people who make the decisions on where to place these will be in contact with the local authorities. The local authorities will need to find which areas are suitable for these peaking plant installations and so on. So it's all a very integrated set of complex decisions that need to be made. Digital twins are definitely one of the tools that are going to be key in making sure we make these decisions as optimally as possible.
Certainly. And Arvind, now, if you talked about peaking plant, there are also plants such as CCGTs which consume larger quantity of gas, right? Mostly distribution connected or transmission connected. But if you compare between CCGTs and peaking plants, why are CCGTs not? Would CCGTs create the same problem?
So firstly, there are two, maybe just to explain that, there are fundamentally two type of gas turbines. There are the so-called combined cycle ones, GT, which kind of use the heat which comes out of the primary turbine to then drive a second system to increase efficiency. And then there are so-called cycle turbines where you just have gas burns, goes through a turbine, drives that, and gets a lot of heat gets emitted on the other side. The CCGTs are very efficient, much more efficient, but they have higher capital costs, whereas the OCGT have lower capital costs but are less efficient. And that's why they are often used for peaking plants. So firstly, we should probably distinguish between peaking plants and kind of more long-running baseload plants. The reason that we're not that worried about baseload plants is because they agree typically a day ahead at least, often weeks or months in advance when they're going to generate electricity. And so they need to nominate to the gas distribution company how much of that gas they're going to consume every day. And so they can plan for them. So that is kind of an established practice already. Where the challenge with the peaking plants is that they can be dispatched at very short notice and therefore cause kind of potentially unforeseen problems on the gas network. Clearly, both are important. So the bigger plants that run more constantly or at least more predictably are causing less of an issue at the moment than the other plants.
Peaking plants are sort of intermittent generation sources for.
Indeed, yes.
Yeah. So James, when you talked about these different personas, you talked about Helen persona, Roger persona, you talked about Barbara, and all those things. It's data exchange, right? If you want to simulate these different capabilities of how peaking plants might generate, or even when peaking plants would really come online and you want to show something to companies, how are you managing this data interaction between many stakeholders, and how about data transparency on, especially if you have this diverse set of personas talking to one system?
Yeah, so we've used IBM App Connect Enterprise. We've created flows between the different production and consuming systems. So it's a low-code, no-code environment. This actually allows us to create these flows and transforms in very quickly. I think that's hugely beneficial here because we're prototyping, we're experimenting, we're able to iterate very quickly and get feedback from our sponsor users very quickly. So I think it's a really powerful technology to be using for something like this.
Okay, and I'm focusing on the IBM value engineering method. So what is your approach for engineering this solution?
Okay. Yeah, when we talk about the IBM value engineering method, we have two stages, the innovate stage and then the co-create stage. So the innovate stage is all about defining the value, and the co-create stage is all about proving the value. So in the innovate stage, you led a piece of work there to capture Epic's user stories and features with domain experts, building that, capturing a map of information in a way that is suited to modern agile product development, and then prioritizing those user stories with partners, and then starting to add clarity to that by building some basic interaction diagrams, some component models, and I think helped us to develop some of those core functional requirements. That was really the first stage. That was the innovate stage, and I think that then gave us it led us to a place where we could then start to build, and we working in sprints. So first sprint was focused on Alex. The second sprint has been focused on Helen and Roger, and we're now iterating on different personas to incorporate the feedback that we're getting, and really kind of trying to reveal some of the challenges that there are in these areas to test our assumptions. The other thing I'd add to that is the work we've been doing has raised some really useful insights into different areas, 3 different areas perhaps. So one of those areas being around the access to kind of open energy data. So we would want anyone with kind of legitimate reasons to access the right data to be able to do that, both internal and external users. The other area is in around improving the visibility and capacity to make better formed decisions. So I talked about Alex and the ability for him to understand how to produce hydrogen most efficiently, and then enabling those kind of what if scenario simulations. And our third area is around connecting and interoperating multiple digital twins. So we've shown the interaction between Helen and the gas twin. So we're starting to see how different digital twins might start to interact in this future energy ecosystem.
Yeah, certainly. And I do remember when we were writing these epics, and how easy it was for every one of us to slide in different direction, because once you have thoughts and then you start expanding, you're a person who were keeping us focused on the scope of this particular project, isn't it? And I really like that guidance on if we are diverting away from, or if we are going down the rabbit hole, how you say that, okay, let's focus on what we have to deliver at this alpha phase, and then let's keep discussing and dividing and conquering it in phases by phases. That was really good experience when you talk about such a big scope of work. Delivering two twins in 6 months' time is a big challenge. Even small 1 or 2 use cases within it's a big challenge. And then defining the scope, defining the project approach, and getting it to a certain stage presentable is a big thing to start with. And I really like that approach that you always took to keep everyone in line.
No, thank you, Nina. That's very kind of you. I mean, it is a difficult challenge because on the one hand, we want to be agile and we want to be able to act on new information that comes up. But on the other hand, we have to ensure that within the very limited scope or budget and timescales allowed within the alpha phase, we deliver something that's useful. And I think the thing that there are questions I asked time and time again of both myself and of the team, and I haven't got a written down list, but the first one is how's this going to help somebody make a better decision? So doing stuff that isn't going to help somebody make a better decision was kind of deprioritized. And then the second thing is can we actually build this? So And I think we did a whole bunch of stuff which we couldn't build, but we didn't spend more time than kind of writing down some pretty cool requirements, but ones that we knew up front we weren't going to build.
Certainly.
The other thing was we got some pretty good feedback from UKRI, and we know ourselves that the importance of this is not building the most clever digital twin of a system that's totally internally focused. This is an alpha phase. This is not we're not actually delivering a digital twin that anybody will use in anger. This is to demonstrate concepts. And one of the biggest, most important concepts we wanted to illustrate was how we interact with the outside world. So by asking the question, how does this use case, user journey, feature demonstrate or test how we communicate, integrate with other digital twins, communicate with the outside world? I think was the other question that really helped us to focus on the key challenges that we were trying to address. Now, a different digital twin might have different challenges, but those were the ones that we set out from the start. And I think we've been pretty consistent in asking those questions of ourselves time and time again to help, on the one hand, allow innovation and so on, but on the other hand, keep our focus on what we set out to do.
Certainly. And then once requirements were captured, then translating into architecture, I think, James, approach that you had considered, right? Component model, and then you drew those flow charts, right? Data exchange flow charts. I think that was quite a good step to move from the functional requirement level to that architectural level, isn't it? I like that particular approach of how easily you were able to translate those things. Can you elaborate on that approach again?
Yeah, so the interaction models diagrams show the flow of, or show the interactions between the main functional components. So I think the interaction diagrams on this project, they really help to bring alignment across the different stakeholders. And I think it's easy to think that everyone was in agreement and on this. And I think as we got into this and started talking about interactions, we soon realized that there were in some cases very different ideas about what that future ecosystem and those future interactions might look like. So getting together in York Road, IBM York Road, with partners and developing these interaction diagrams, I think really helped to align us, test assumptions, and as you say, move the conversation more into kind of what components we need, and then in a position really then to kind of talk with our admin team, our build team about the sprint.
Nice. I know we are up the time, and I would say thank you, James and Irving, for taking out time. I know we have extended for 15 minutes, but then this is such an interesting topic to talk about, right? And it's a future that we are building, and there's a lot of innovations going around, and no time is going to be limited. We can keep talking about this for 8 hours, 9 hours non-stop, but then we'll have to stop somewhere. But I really like that you both joined me as a guest on my podcast, and it's really a big pleasure for me to talk about this innovative topic of gas system of future digital twin project that I should say we are building together along with the big team that we have. And I wish everyone a big success on this, and I wish that we get into the next phase with a much bigger and stronger use cases.
Well, thank you for having us, Ninad. Been good talking.
Thanks, Ninad.
Thank you, James. Thank you, everyone.
All right.